Now let's look at this example. This is the system of linear inequalities. 2x plus 2, x plus 2y greater than equal to 10. So this boundary should be a solid line, right? Not dashed line. And this is the second inequality is the 2x minus 3y greater than 6. So the boundary for this inequality should be a dashed line, not a solid line. Okay. So now we still go. Let's still look at the first inequality. So we still need to find the boundary, so which is 2x plus 2y equals 10, right? So we pick arbitrary 2 point. For example, we can pick x equals 0, y equals 5. That's the 1 point, right? And we can pick x equals 2, y equals 4. This is another point, right? So you just pick arbitrary point for your convenience, right? But it should satisfy this, on this line. Let's draw the graph. This graph not good. Okay. So this is 0, 5. So x equals 0, y equals 5. So this is 5. 1, 2, 3, 4, 5. So which is here. And x equals 2, y equals 4. 1, 2. So y equals 4 is here. Then we connect these two lines. Okay. Then we pick up arbitrary point. So which region belongs to this inequality, right? So we use a solid line because here is the greater than equal to. So the boundary is included. So which region? We pick arbitrary point, okay? We can pick the origin, right, if you want. No, this time I don't want to pick origin because the origin, yeah, of course, if the origin is the easiest way, right? Well, let's just pick origin. Okay, so it's 0 plus 2 times 0, which is equal to 0. Greater than equal to 10? No, this is wrong. Okay, so this region is not the region. So this would be the region. The region containing 0, 0 point is not the solution region. So the upper region, upper half plane, would be the solution set. So now let's look at another one. 2x minus 3y greater than 6. 2x minus 3y greater than 6, right? Okay, so we still look at the boundary, which is 2x minus 3y equals 6. But here, since this is greater than, so the boundary should be a dashed line. So that means the boundary is not included, right? This line is not included. So here is, we pick arbitrary 2 point, okay? 1 point is x equals 3, y equals 0. X equals 0, y equals negative 2, right? So this is the intercept, y-intercept and x-intercept, right? We use another color. 3, 0, 3, 0, 3, 1, 2, 3, 3, 0 is here. And what is 0, negative 2? Negative 2 is here. 1, 2. Then we connect these 2 points. We use the dashed line because the boundary is not included, right? Okay, so which part for this inequality? So we still pick, since the 0, 0 point, the origin is not on the line. So we still pick the origin. We pick 0, 0. We plug in, then you will have 2 times 0 minus 3 times 0 equals 0, greater than 6. Is that true? No, this is wrong. Okay, so in other words, the half plane, upper half plane containing this origin is not on the solution set, so this would be this part. Sorry. So this part, right? Okay, so where is the common part? This is the common parts. Use the purple line. One side is solid, the other side is dashed line. So this side is included. The solid line means the solution on this side is included on this boundary, and the dashed line means the solution on this side is not included. And this is the common parts. And this boundary is unbounded, right? You can extend this side forever. So this is the unbounded. And this is the corner point, okay, which is, if you do the calculation, you will see that if you put these two equations together to form a linear system, these two equations to form linear system, then you solve this linear system, you will see this corner point, which is equal to, which is 6 and 2. Okay, this is the corner point. Okay, so now let's look at some application problem. So now let's look at this example application problem. A furniture company builds dining tables and chairs. Let X denote the number of chairs produced in a week, and Y denote the number of tables produced in a week. Suppose a table requires 8 labor hours of assembly and 2 labor hours of finishing. And also suppose a chair requires only 2 labor hours of assembly and 1 labor hour of finishing. The company can pay for at most 500 labor hours of assembly and 160 labor hours of finishing. The first question is, set up a system of inequalities to model this situation. Then find the feasible region in the plane. The feasible region means the solution region, okay? That means all the points, the region where all the points in this region satisfy this system of linear inequalities. So for this problem, let's draw a table to help you to summarize the problem set, what the problem set. So we draw a table. So this is the chair. The first row is chair. The second row is table. Okay. The first column is quantity. So chair is X chairs and Y tables, right? This row is the assembly. So chair need 2 labor hour. So it's the total is 2 times X labor hours for chair for assembly. And the table need 8 labor hours. So it's 8Y. The next row, a column is finishing, the labor hour for the finishing. And the chair need 1 labor hour of finishing, so it's 1 times X, so it's X hours. And here is the 2 labor hours of finishing for table, so it's 2 times Y hours. Okay, so now we need to set up the inequalities. The first inequality, so this is from the last sentence for this problem. The company can pay at most 500 labor hours of assembly. Okay, assembly is the total hour, which is 2x plus 8y. This is the total assembly hours, right? But at most 500, so you cannot exceed 500. So less than equal to 500. Then the next one, which is x, the labor hour for the finishing, which is x plus 2y, right? And at most 160 labor hours of finishing, so it cannot exceed 160, so it's less than equal to. So these are two inequalities. And remember that when we talk about the quantity for the chairs and tables, we set x, so x must greater than equal to 0, right? It could not be a negative number. And y is also greater than equal to 0, right? So you put together for any real problem, don't forget these two conditions. Okay? So now this is the linear system of linear inequalities, right? We have 4 inequalities. So this is the first problem. Set up a system of inequality to model the situation. So this is the model. Okay, let's erase this box. Okay, so this is the problem. So this is the part A. So sometimes use a table to help you to understand this problem. Okay. Problem part B. Find a feasible region in the plane. Feasible region means the solution region for this linear system, linear inequalities. Okay. So now let's draw the graph. So it's let's look at the first one. 2x plus 8y less than equal to 500. Okay, so this is a large number, right? 500. So the scale of the xy plane should be different. Okay, so now let's look at, so since this is the equals 500, let's choose this one, right? So if we let each one is 10, this is 1, 20, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so this is 10, 20, and so on, right? And so this is the 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. This is 10, 20, and so on. So we can pick arbitrary 2 points, right? So we should choose a good choice. We should take some good choice. When x equals 90, so you plug in, so it's 180, right? For here, 180. So 500 minus 180 equals 320. Then divided by 8, so y equals 40. So 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 9. And 4. 1, 2, 3, 4, 40 here. So this is the 1 point, right? And another point is if x equals 50, so it's 2 times x equal to would be 100 minus 500 minus 100, 400 divided by 8, so y is also 50. So 50, 50, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. And here 1, 2, 3, 4, 5. Right? If you connect these two. Okay, so this is the graph. And this is less than equal to, so this boundary is included, right? So let's pick a 0, 0 point because 0, 0 is a very easy point to test. So let's pick 0, 0 point to test. Okay, so we put 2 times 0 plus 8 times 0 less than equal to 500. Yes, of course, this is true. So this would be the region. Let's look at the second one. We use the red pen. The second one is x plus 2y less than equal to 160. X plus 2y less than equal to 160. So we still look at the boundary. This boundary is solid line because it's less than equal to. So its equal sign is included. So we have 2 points, right? We still choose x equals 60, y equals 50. This is 1 point, right? 60 and 50. So 1, 2, 3, 4, 5, 6, 60. This is 60. And 50. 1, 2, 3, 4, 5, 5 is 50. So would it be here? This is the 1 point. Okay, so now another point. X equals 40, for example. 40, so y equals 60, right? 40, 60, 40. 1, 2, 3, 4, 40. This is 40. 60 is here. So what will be here? If you connect these 2 points, my line not good, but just for illustration. Okay, so that's the red line. Okay, so which part? We still notice that this, we still use 0, 0, right? It's very easy for us. We test 0, 0. So 0 plus 2 times 0 equals 0, which is less than equal to 160. Yes, correct. So it should be the plane containing the 0, 0 point. So we use an okay. So now, when students will stop here, they say, okay, this is the common parts, right? But they forget there is another two, x greater than equal to 0 and y greater than equal to 0. X greater than equal to 0, that means above x-axis, right? So we use another color. So which is above x-axis. So this is x greater than equal to 0. Above x-axis. Y greater than equal to 0. On the right side of y. Sorry, x greater than equal to 0. Yeah, sorry, this yellow line is y greater than. Sorry, this I made a mistake. So this is the y greater than equal to 0, above x-axis, right? And green, which is x greater than 0, so right to the y-axis. So you can see which region contains 4 colors. I use this one. This is the region, the feasible region. Okay, so this is the feasible region. And this feasible region, we notice that it's bounded, not unbounded, because this side will go down, and somewhere it will intersect x-axis. I cannot draw anymore. Okay, somewhere will intersect x-axis. So there is an intersection point. Right? You can go down somewhere. It will intersect x-axis. So at last there is a closed region. It's bounded by the lines, 4 lines, right? So this is the bounded region. Okay, so this is this problem. So be careful for the problem in this section. I know that it will cost time for each problem. Okay.